Hello and welcome back. In this video, we're going to take a more formal look at the wedge product. So this is a follow-up to the first video, which was titled Wedge Product. And this follow-up will take a more formal stance. All right, so the wedge product, also known as the exterior product, is a fundamental operation differential geometry and algebra that allows us to construct high dimensional objects called differential forms from vectors or lower dimensional forms. The wedge product is particularly important in the study of differential forms, and it plays a crucial role in calculus on manifolds. Hence, you can imagine its use in general relativity, including areas such as integration on manifolds and Stokes' theorem. It also goes beyond those, but that's enough to say for now. So let's make a start. And maybe I'll just hide this as well. All right, so let's start with the definition. So remember, this is a more formal follow-up to the first video. The first video is more just a basic introduction. Anyway, given two differential forms, omega and eta of degree p and q respectively, i.e. omega is a p form and eta is a q form, the wedge product, omega wedge eta, is a differential form of degree p plus q. Now, the wedge product is bilinear, anti-symmetric, and associative, and we'll go through that later. Anyway, but mathematically, if omega is a p form and eta is a q form, then omega wedge eta is a map from the tangent space of p plus q vectors to the real. So where TPM is the tangent space of the manifold of the point P, is the tangent space of the manifold M at the point P. And the wedge product of the P form omega and the Q form eta is a P plus Q form that takes as input P plus Q tangent vectors, P plus Q tangent vectors from the tangent space at a point on the manifold M and produces a real number. All right, so the wedge product, omega wedge eta, is a P plus Q form that is defined to be, here's our formal definition. This is why this video is different to the last one, which was just a more basic practical introduction. So omega wedge eta, and then it's taking these P plus Q vectors, all right, and then we're going to expand these out. So omega will take P vectors and eta will take Q vectors, all right, and there'll be this sign factor out front, and we're going to be looking at all of this, the different parts of this definition. But as you can see from the first video and from others on 1 forms, 2 forms, 3 forms, we now understand the idea. You can see that these are so many vectors we're taking depending on the degree. Okay, so P of them for the P form omega and Q of them for the Q form eta. All right, and then we just need to have a look here. There's sigma, S, this factor here, and we're going to treat all of those separately and look at each one in turn. We understand what the sigma is, the sum. Remember, there's combinations of these. So if omega were a 1 form, there'd be 1 vector here, and eta a 2 form, there'd be 2 vectors here. And when we expand this out, we'll have 6 terms. Okay, so then we need to ask ourselves, what is this sine sigma? And which is of course just going to be the sign, will be a plus or minus 1. And this here, the symmetric group here, what on earth is that? We'll have a look at that in a minute. And this factor out here to normalize it, rescale it, so to speak. Okay, so S subscript P plus Q is the symmetric group on P plus Q elements, and sine sigma is the sign of the permutation sigma. Okay, so as I said, if omega was a 1 form and eta a 2 form, then you're going to have a 3 form produced, and you'll find that there are 6 terms here when we expand this out. Now, the properties of the wedge product. So anti-symmetric, very, very important. I'm just going to quote this property first, and then I'm going to look at in detail these factors here, what these things mean. The wedge product is anti-symmetric, meaning that if you swap 2 forms, the wedge product changes sign. Now, in general, for P and Q forms, omega wedge eta would be -1 to the power of P times Q, and then the reversed order of eta wedge omega. And order does matter in this, it's very important. And whether or not this is a plus or minus out front is given by this sign here, and we're going to look at more of this later as well. So for example, if omega and eta are 1 forms, then omega wedge eta is equal to minus eta wedge omega. Right, this orientation, as we've seen, this relates to orientation, matters. It's important. All right, so let's look at the symmetric group first. So symmetric group S subscript P plus Q. So symmetric group SP plus Q is a group of all possible permutations, rearrangements of the P plus Q elements. So for example, if you have three elements, 1, 2, 3, then the symmetric group S subscript 3 would include all the possible ways to rearrange these three elements. So 1, 2, 3, no change. And then swapping 2 and 3, we have 1, 3, 2, and so on like that. Notice there's 6 of them here. So S subscript P plus Q includes all such permutations of P plus Q elements. Now, permutations and the sign of a permutation, because remember, reversing orders changes the sign. So a permutation sigma is essentially a specific way of rearranging or ordering a set of elements. So in S subscript P plus Q, each element sigma is a particular permutation. All right, now the sign of a permutation, denoted sign of sigma, tells us whether the permutation can be achieved by an even or an odd number of swaps, transpositions. Remember earlier I talked about swapping the 2 with the 3. Okay, that was one swap, that's an odd number. The sign of sigma would then be -1. So if sigma can be achieved by an even number of swaps, then sine sigma is +1. And if sigma requires an odd number of swaps, such as the one I just demonstrated, then sine of sigma is -1. So for example, consider the permutation sigma equals 2, 1, 3 of the set 1, 2, 3. Now we can get from 1, 2, 3 to 2, 1, 3 by swapping 1 and 2, a single swap. So sine of sigma is -1. On the other hand, the permutation 3, 1, 2 can be achieved by swapping 1 and 3. Okay, so 1 and 3, and then swapping 2 and 3. All right, so 2 swaps, an even number, and so sine of sigma is +1. All right. Now the role of the symmetric group and sign in differential forms, as you picked up in the previous videos, it does matter. Swapping terms does result in a different orientation. So in the context of differential forms, when we write an expression involving wedge products like dxi, wedge dxj, and we want to permute these differentials, the sign of the permutation is crucial. If we have a wedge product of differentials, say dx1, wedge dx2, wedge dx3, and we permute the order, the result will change by a factor of sine of sigma, where sigma is a permutation we applied. So for example, permuting dx1 wedge dx2 to dx2 wedge dx1 gives minus dx2 wedge dx1. It's just one swap, so the sign of that swap is -1, because swapping 2 elements is an odd permutation. Remember, it was 2 elements have been swapped, it's one swap. Symmetric group S P plus Q, subscript P plus Q, represents all possible ways to permute P plus Q elements. Okay, so if you've got 3 elements, there's going to be 6 different ways of doing it. Sign of a permutation, sine of sigma, indicates whether a permutation involves an even +1 or odd -1 number of swaps. All right, now let's look at the role of this factor 1 on P factorial Q factorial in the original formula here. Now this factor plays a crucial role in ensuring the wedge product of 2 differential forms is anti-symmetric and properly normalized. So ensuring proper normalization. So let's have a look at what that means. So when taking the wedge product, omega wedge eta of a P form omega and a Q form eta, we are combining them into a P plus Q form. The resulting form, okay, remember here we've got P vectors and Q vectors, so P plus Q form. So if eta was a 1 form, and if omega was a 1 form and eta a 2 form, then this will produce a 3 form. All right. So 1 plus 2 is a 3 form. The resulting form should have the correct scaling and normalization properties. So the number of permutations of the set 1, 2 up to P plus Q can be very large. Specifically, it can be P plus Q factorial is what it is, that permutations. And when we write that out, that's what we get. So if this is a 1 form and that's a 2 form, we end up with a 3 form, and the permutations, there's 6 of them. Okay, some with negative signs, some with positive. Okay. However, in the wedge product, we only want to count distinct contributions without over-counting. And this is where the normalization comes in. normalization, rescaling. To achieve this, we divide by the number of ways to permute the P indices within the first P slots, which is P factorial, and the number of ways to permute the Q indices within the last Q slots, which is Q factorial. All right, that's the factor 1 on P factorial Q factorial accounts for these internal permutations. So if you've got two groups, red marbles and blue marbles, and you want to look at all the different permutations of them, and they're all numbered, say, from 1 to whatever, then when you do if you've got 10 of them, you do 10 factorial. But the thing is, you've got elements that are the same color. So they've got to be permuted within the red ones and permuted within the blue ones. So you get this factor that you've got to take into account in order to get distinct ones. So the factor 1 on P factorial Q factorial accounts for these internal permutations, ensuring that each distinct pairing of P elements from omega and Q elements from eta is only counted once in the sum over permutations sigma. All right. The anti-symmetry preservation, the wedge product is defined to be anti-symmetric. This means that if you swap any two of the input vectors, x1, x2 up to xp plus q, the sign of the wedge product should change. The factor 1 on P factorial Q factorial helps to maintain this anti-symmetry by correctly weighting the sum over all permutations. All right, each permutation sigma is multiplied by its sign of sigma, because the wedge product should account for all possible rearrangements of the P plus Q vectors, including their inherent anti-symmetry. The 1 over P factorial Q factorial factor ensures that the sum properly reflects the contributions of each permutation without introducing any bias or redundancy. All right, just to try and make this a little bit more real, suppose omega is a 1 form and eta is a 2 form, then omega wedge eta is a 3 form. The number of permutations of 3 vectors, remember it's a 3 form, it takes 3 vectors as its argument. The number of permutations of 3 vectors is 6. So 3 factorial is 6. 3 times 2 times 1 is 6. But internally there are 1 factorial equals 1 ways to permute the single vector in omega, remember it's a 1 form, and 2 factorial equals 2 ways, eta is a 2 form, to permute the 2 vectors in eta. So the factor 1 over 1 factorial 2 factorial equals a half ensures that when we sum over all 6 permutations, we don't overcount the internal structure of omega and eta. I have talked about this in one of the previous videos when we were looking at 2 forms. I think it's in the video on introduction to 2 forms. Now, this business of permutations is not the subject of this video, but this link here has a good look. Permutations are multi-sets. You can have a look at blue and red marbles and that sort of thing. So have a look at that, and I'll put it in the description to the video below. I'll put this link, that is. All right, so in summary, here's our formula again. So we've accounted for the sigma, the sine sigma, the symmetric set, and this factor here. So the 1 on P factorial Q factorial factor in the wedge product formula normalizes the result by avoiding overcounting of the permutation basis forms within omega and eta, and preserves anti-symmetry by properly weighting the contribution of each permutation according to its sign. And for a specific example of that, have a look in the introduction to 2 forms. Now, this factor ensures that the wedge, that's the video of introduction to 2 forms, sorry. This factor ensures that the wedge product of 2 differential forms behaves correctly as an anti-symmetric P plus Q form. All right, now let's come back to the factors. Remember, I started with anti-symmetry, and then I interrupted the properties of the wedge product in order to have a look at the various aspects of that formula. Let's come back now in general, because we're still going to consider bilinearity and associativity. So the wedge product is bilinear with respect to addition and scalar multiplication. So alpha, beta, omega, and eta are differential forms, and C is a scalar. Then alpha plus beta, in parentheses, wedged with omega, is we could distribute both those forms across here. So we get alpha wedge omega plus beta wedge omega. Okay, so it's bilinear in that respect. And multiplication by scalar, omega wedge, the scalar C times eta is just C times the whole lot, omega wedge eta. Associativity, the wedge product is associative, so this condition holds. All right, now let's have a look at the wedge product in a coordinate basis. So in local coordinates on an n-dimensional manifold M, so some local open set U on M. So in local coordinates x1, x2, xn on an n-dimensional manifold N, we can express a differential one form omega as omega is this here, okay? Where omega are smooth functions and dxi are the coordinate one forms. Now, this I will go up to n, can go up to n, according to the dimension of the manifold. All right. All right, the wedge product of two one forms, omega and eta, in these coordinates is given by omega wedge eta, is this object wedged with this one, summing here over I, summing here over j. Expanding this using bilinearity, we'll end up with this. Omega wedge eta is the sum ij 1 to n up to here. All right. Now, because of the anti-symmetry of the wedge product, dxi wedge dxj is minus dxj wedge dxi, and dxi wedge dxi, where these are the same, is 0. So let's have now, for the rest of this video, we're going to look at some examples. So let's start with the wedge product of two one forms. Let omega be f of xy scalar function f dx, and eta be g of x scalar function g dy. Then omega wedge eta is f times g dx wedge dy. Here dx wedge dy represents an oriented element on the two-dimensional manifold. See the introduction to two forms for all that. The wedge product of a one form and a two form, that omega equals dx and eta equals dy wedge dz, and omega wedge eta is dx wedge dy wedge dz. By associativity, that's the same as this. And you could drop the parentheses altogether and write dx wedge dy wedge dz. By the associativity of the wedge product, wedge omega eta equals, and look at it, I've already said this, you remove the parentheses, you just have this. Now this represents an oriented volume element in three-dimensional space, and if you have a look at the introduction to three forms, you'll see that there. But just note, swapping two of these basis one forms, just taking omega and wedging it with itself, omega in this case here, omega wedge is minus omega wedge, so that implies that omega wedge omega is 0. And we're going to see that where you're dealing with the odd case, as in omega is a one form, this holds, and so wedged with itself, it will be 0. In other words, dx wedge dx has to be 0. All right, but as you can see, dx wedge dx, see omega is dx wedge dx is equal to minus dx wedge dx. Well, the only way that can be true is if the wedge product of these two is 0. All right, given the mixed two form and one form, so omega is f dx wedge dz and g xy dy, okay, on R3, let's compute the wedge product, omega wedge omega. Well, here we go, a little bit of calculation in these parts, just want to show a couple of things. Omega wedge omega, here we go, writing that out like that. Expanding this using the distributive property of the wedge product, we get this. So this one times that one, so we get f times f, dx wedge dz, wedge dx wedge dz. I'm putting this underneath, you'll see why in a moment, plus f times g, dx wedge dz, wedge dy, g times f, dy wedge dx, wedge dz, g times g, dy wedge dy. Okay, well, dx wedge dz, wedge with itself again is 0. You can see, look, anything here, I mean, shift these about, you've got dx wedge dx there, 0. Okay, anything, something wedged with itself is going to give you 0. And you can simply permute these to see that that is the case, equals 0, because the wedge product of any form of itself is 0. dx wedge dz wedge dy, okay, by the associative, you can, by moving this around, if I move that one spot, this becomes negative. If I move it again, the negative becomes positive, and I can show then that dx wedge dz wedge dy is the same as dy wedge dx d wedge dz. So that's interesting there, and we'll use that in a moment. All right, number 3, dy wedge dy is 0, because the wedge product of one form in itself is 0. This leaves us with, putting all that information in, omega wedge omega with itself is 0 for the first term, 0 for the last one because of that bit on the end there. And then we're left with this bit, Okay, and as we've already discovered, you can see that we've altered this one actually. I think it was wedge dy in the end. We brought it over here, and so we've got equals 2. Okay, so it's not always 0. One of them was odd, one was even. Okay, so it's not always the case it's going to be 0. All right, now given the one form, odd omega, this is a one form on R3. Let's compute the wedge product, omega, wedge, omega. So writing it out, here we go, like that. Okay, so expanding that out. Okay, we have this plus that one, then that with that, and that one wedge that. Well, you know dy, wedge dy is going to be 0, dx, wedge dx will be 0. So first term and fourth term will be 0. We're left with 2 in the middle. All right, so just writing it out again, okay, you can see that one's going to be 0 and that one's going to be 0. So we'll put that there, 0, 0. And then we're left with these, the second and the third term. Now, see with this second term, we've got dx wedge dy, f times g, g times f, the scalars, same thing, f times g equals g times f. But we can change the order of this, all right? And what do? I'll change the order of this one, sorry. So if we swap these basis 1 forms, so we get dx wedge dy, we have to put a minus sign out front. So f times g, dx wedge dy, minus g times f, dx wedge is 0. Okay, so in general, what you'll find is that if omega is a k form of odd degree on Rn, then omega wedge omega is 0. So from omega wedge eta equals minus 1 to the power of p times q, and then reversing the wedge product, eta wedge omega, okay, that holds. But when eta equals omega with p equals q equals k, because omega is a k form, whatever value k is, so p and q must be the same, we get omega wedge omega is minus 1 k times wedge omega wedge, which is equal to minus omega wedge omega, or it should be, but it equals 0 so long as k is odd. So for all these odd ones, this will be minus. Okay, if you put 1 in here, 1 times 1 is 1, minus 1 to the power of 1 is negative 1. And the only way omega wedge omega equals minus omega wedge omega is if it equals 0, if the wedge product is 0. And that happens for the odd numbers, where k is odd. Next one. All right, so given the 2 form, this omega f dx wedge dz plus g dy wedge dz on R3, let's compute the wedge product, omega wedge omega. Well, here it is like this, writing it all out, and this time I'm just going to drop this function of f of xy and just put f. Same with g. Okay, expanding this out, f squared here, all of this. Now you can see dx here and dx here, that's going to go to 0. Dx here, dz here, dz here, you know that's going to go to 0. And you've got here dy, dz again will go to 0, dz again goes to 0, the whole thing is 0. Now, will that always be the case though? Because this is an even value. It's a 2 form, but it happened to work out 0. Now, given the 2 form, omega is f dx wedge dz and g dy wedge dw on R4, because we have 4 coordinates, so it must be on R4. That's the minimum it can be on. We can't have this on R3 because we've got 4 coordinates, so that's not possible. So let's compute the wedge product omega wedge omega, and we have here, writing that out, I think I've rewritten that one again. Yeah, here, I've written it all again, just so you don't have to flip back to the previous slide. And we get f squared here, we get all this, look at that, dx, dz, dz, well, that's going to drop out. This one here, dx, dz, dy, dw, they're all different, so that's okay. Plus gf, and they're all different. Plus g squared, well, dy, dy, dw, dw. So first term and last term will be 0, 0, and 0. And then here, we're going to have, well, let's see if we can rearrange this. We've got dx here. If I swap dy in front here, and then I'll have dz, dw, so I only need 1 swap, so that makes that negative. But this second one here, I need to swap dx to one place. That's 1 swap, so it makes it negative. I then need to swap it again to put in front of dy, so that makes it positive. But then at the back, I've got dw, dz, and I need to swap that again. So there's another swap. So overall, odd number of swaps, 3 of them I think it was, I get minus. So I end up with 2 lots of fg times all this. So it's not 0, even though we started out with omega being a 2 form, an even form. So it's not, in the case of even, not always 0, but with the odd numbers it is. All right, I hope that helps everyone. I'll see you in the next video. Thank you very much for watching. And please, if you will, push the like button and subscribe. And I hope to see you in more videos. Thank you, everyone. Take care. Oh, I'm back now. Look at that. Sorry about that. I'd just like to thank you all again. Please subscribe and push the like button if you will. Thanks. I appreciate it if you could. I look forward to seeing you in the next video. Okay then. Bye.